Okay, well, I'll just get started. So Lucas asked me to talk about sparsity. So this meetup is all about intersection between neuroscience and machine learning and how we can learn from neuroscience to impact machine learning. And so today's topic is sparsity, and what I thought I'd do is just give a review of sparsity in the neocortex. And what I'll focus on is just kind of experimental data, and then the rest of the talks I think are more machine learning focused. So I'm not really going to touch too much on theory, although I'll have some opinions along the way. We can get going. So I'm Subutai Ahmad. I work at Numenta. You can follow me on Twitter there. But more importantly, this video here was taken by Professor Hassan using a recording technique called optical imaging and calcium imaging, where he's looking at the kind of firing of neurons in a mouse. I think this is somatosensory cortex or touch cortex, as the mouse is engaged in an active task. And so, as you can see, there's neurons firing all over the place, but it's pretty sparse. And your neocortex is looking like this now, as you're listening to me talk and paying attention to this stuff. This is basically what's going on in your neocortex.
What are the dimensions of that?
This is just X and Y. It's just like a 2D optical plane. So that basically.
Is that thing very, very, very small? Or
yeah, it's probably like about 30 microns wide there. So, that. So yeah, there's probably a few hundred neurons in here, but only a few are active at a time. Okay, so in general, if you think about the neocortex, well, maybe real basics. How many of you know what the neocortex is? Okay, most of you do. It's kind of the largest organ in the brain, and it's the seat of our intelligence. And all mammals have a neocortex, and only mammals have a neocortex. And there are many different areas there that are thought to control motor functions, sensory functions, thought, planning, all that stuff. But so there's all of these different things that our neocortex is responsible for. But in the neocortex, sparse representations are critical across all sensory modalities and across all of these functions. So no matter what the neocortex is doing, it's always using sparse representations to do the work. Okay. And sparsity is really deeply ingrained into the neocortex in really surprising ways that I'll try to touch on here in this talk. And I think you can't really understand cortical function without understanding sparsity. So if you're interested in understanding neuroscience principles and how it might impact machine learning, I think sparsity is a real nice place to start, because there's already some sparsity in different parts of machine learning. But sparsity is very, very deeply ingrained in the neocortex. Okay, so what exactly is sparsity? And it's basically when something is mostly missing. You have some some quantity of measuring, and it's mostly not there, just a little bit is there. If you think about a sparse vector or sparse matrix, it's one where most of the elements are zero, exactly zero, so almost like they're not there. In the neocortex, if you look at the papers, they describe at least 3 different types of sparsity. So the first one is population sparsity. So that's kind of what I was showing there now. If you look at a collection of neurons, how many are active right now? And generally, it's a small percentage of the neurons are actually active. Then there's this weird one called lifetime sparsity, which is if you look at a single neuron over its lifetime and all the stimuli it's getting, how often does it actually fire? And it doesn't fire that often, so that's a type of sparsity. I'm not really going to touch on that. It's a little ill-defined and impose this definition, because you kind of have to average over all possible inputs that it could ever see. And for any given experimental paradigm, you're only going to see a small subset of inputs anyway. So that's another definition that's you see in neuroscience. Another one is connectivity. So connectivity in the neocortex is really sparse. So whenever you have a group of cells or a layer of cells that project to some other neurons, if you look at what are the percentage of cells that are actually physically connected, and that the connection probability is usually fairly small. So these are 3 types that are the most common types you see. But there's actually there's more, and I'll get to them in a bit. Sparsity actually goes deeper than these things, but I'll just try to briefly give you some flavor for some of these things. So population sparsity is the percent of neurons that are firing right now. It's a little hard to measure. In order to know what right now is, you need to define a window of time to measure in. So the ideal window from a neuroscience perspective, is about 5 milliseconds, but that's often quite hard to measure. Many measurement techniques actually look at 75 millisecond time bins. So it's actually somewhat hard to really measure this properly. And the denominator is often unknown, because with some technique you get some subset of neurons, but there's a lot of neurons you're not recording from at any point in time. But still, people estimate that roughly about 0.5% to 2% of the cells are active at a time. Okay, so it's very sparse. It's obviously far sparser than most neural net machine learning techniques. So I'll give you a quick example of a data set here. So this is data that we collaborated with Spencer Smith in UEU, when they were at the University of North Carolina. He's now in UCSB. So what they did was they recorded this video from a mouse's perspective. So they took a camcorder and literally moved it around their cage. So this is a naturalistic video. And what they wanted to do was record sparsity over time. How the sparsity changed as the mouse is looking at this video. Okay, so this, if you read neuroscience papers, a lot of times they'll do kind of oriented bars or gratings or some really simple stimuli. This is a much richer. It's a much more naturalistic stimulus. And what's interesting is that these graphs show the activity of cells. So what it shows here is, if you look at the very first time you see the video is 30 seconds long, and they're recording from about 360 neurons. And whenever each neuron fires, you see a dot. Okay? So during the course of this video, you see that it's a sparse response. Okay? Most of the time, a given neuron is silent. But if you look at the 20th trial, it's actually far sparser. So even though it's the exact same input, the 20th trial is much sparser.
So the mouse is shown the video?
Yes, the mouse is shown the video over and over and over again. So this is the first time it's seeing it, and it's the 20th time. And this is really interesting. So the sparsity is not some fixed thing. It really changes. It's a very dynamic quantity.
Is there any notion of epochs going on, or is there like a clock, or is this just continuous?
Well, there's no clock in the brain, not in the way we think of it in CPUs, but you can think of each presentation of a video as an epoch, if you will. They call it a trial.
Because the input is.
It's a sequence of images. It's just a video I'll show you, and then it shows it over and over again with the blank thing in between. So we actually measured the sparsity over time, and it goes down. And so we have a couple of papers that describe our theory of why this is, but for the purpose of this talk, just know that sparsity is not some fixed thing. It's very dynamic, and as you learn, if you see sequences of stuff, or you learn about some stimuli, you give some complex stimuli, the neocortex often gets more sparse, which is quite interesting. Now let's talk about sparsity and neurons. So this is an example of a pyramidal cell. This is a typical neuron in the neocortex. You can see that it's quite complex. It's got all of these really complicated structures called dendrites, and that's where the inputs come into a cell. The output is the axon, and that's not shown over here. But it's also got all these kind of dendrites up there where it's collecting input. So you can see that the structure is quite complex here. And typically, when we think of a neuron getting input and firing, what's going on is it gets inputs that are usually close to the cell body, and if it gets enough inputs that's above a threshold, it's going to fire something, and that's kind of the typical model. But it's actually much more complex than that. And if you look at the pyramidal neuron again, it's typically got 3,000 to 10,000 synapses or connections. And these neurons are actually sparse computing devices. And the reason I say that is the following. Each neuron has dozens of independent computational segments. In these blue areas, when you look at this dendrite, so it's getting input here, is really functionally segregated into small independent segments. And each segment becomes active if 10 to 20 synapses in that segment becomes active. Okay? So the neuron is actually operating on extremely sparse representations. If you think about it, there's probably thousands of, well, it's got 10,000 synapses, but there's thousands of cells that are sending input into this area, but it's recognizing patterns that are 10 to 20 bits on some sense out of these thousands. So it's very sparse. Yeah.
So there's other synapses on the other neurons like connected to that?
Yeah.
Like when you're saying so 10 to 20, they're corresponding 10 to 20?
Yeah, so 10 to 20 might be like on this little segment here, there might be 10 to 20 synapses that are
But it also responding
co-located.
to another neuron.
Yeah, so synapse is like a weight. So this is the connection. So some other neuron, 10 to 20 other neurons are sending input into this local area here. And if they all become active, or if enough become active, then some event occurs here. Okay. It kind of looks, there's a ton of data on this that if you're interested in.
How does that timing work?
So the timing, these 10 to 20 have to be active within 5 milliseconds. So it's a very precise coincidence of inputs that are detected. And what happens here is completely independent from something that might occur on the other side. So it's not a single monolithic. It's very different from a machine learning neural model. Right? It's not a single linear weighted sum. It's like lots of little independent things. And
after it fires, does it return to a rest state and wait to get
yeah,
more inputs?
sometimes there's a refractory period, and that's a complicated question. There's a lot of dynamics that happens there. Yeah. Go ahead.
If like a segment there fires, do the other parts know that happened?
Generally, no, they're pretty independent. I'll show you actually what it looks like next. Alright, so here's an example, like this little, so some piece gets input, and then what's called the dendritic spike travels to the cell body. I won't go into all the details behind it, but there is some information that flows in. So it's very localized, sparse patterns that are detected in each place.
This illustration doesn't show the continuing convert.
The firing?
Yeah.
Yeah, down here. Yeah, it doesn't. It doesn't. These events don't always cause the pin to fire. Okay. There's another interesting thing about this is that only a small part of the neuron is updating as a function of learning. So the learning itself is very sparse in the neuron. Okay, so learning kind of rules, if you will, looks something like that, but basically the learning is localized to the segment that detected the pattern. So if one little piece detected a pattern and then learning occurs, then that's the piece that's going to get updated. The rest of this is going to be mostly untouched. Okay, so again, that's very different from the way backprop happens. Backprop is global throughout the neuron. Here, it is very, very localized to the specific places. Each synapse or each connection is pretty,
I was just wondering, so the threshold at which the neurons fire and like there are like 10 to 20 synapses for it to like fire, has this gone through some sort of evolutionary process, or is this like common across all human or species?
So everything here I'm saying is on the neocortex, so it's common to mammals.
Okay.
Yeah. So and whether it's mice or monkeys or humans, these numbers are pretty. The numbers so far that I've said are not that different. So yeah.
And is it a possibility that maybe the data is not the firing is not that sparse, but we don't have as advanced scientific equipment to measure minor signals? Is that like a...
It could be. The what's not shown here is the output of the cell. So when the cell fires and an action potential and it spikes, that's a pretty big event. And so no technique is perfect, but we can pretty much detect those.
Okay.
But these other little things, the little events, those are harder to detect.
Right.
Yeah.
Okay.
But so what I was saying is each of these connections or synapses are fairly uninformative. It's the kind of weight, if you will, it's almost like binary. And quite often the synapse won't even become active if input comes in. So it's a kind of a stochastic thing. Neuron can't always rely on it. And its impact is not quite binary, but you can think of it almost as binary. Again, that's very different from neural networks where you have 32-bit precision in your weights. So the synapses are pretty uninformative, and then the way learning occurs is, so you could ask, if the synapse is uninformative, how do you learn? Well, you learn by changing the network structure. So the neocortex learns by adding and dropping connections all the time. Okay. And so the connectivity is very sparse, but the connectivity is dynamic. So it's constantly changing. This is a result that shows how dramatic this is. So here it's looking at one of these dendritic segments over many days, and the red triangles show these synapses or connections that were either added or dropped. And what you can see here is that 30% of the synapses disappeared within a couple of days, and 30% were added. So it's a huge turnover, and so the network structure is extremely dynamic, and it's changing quite a bit.
Does that depend on the age or?
Yeah, it changes less for older people. So when you're young, there's a huge, growth of stuff and lots of stuff dropping and adding, but it is constant throughout adulthood.
But so that I have a very kind of dumb question. What happens if somebody's asleep, deep sleep?
Yes, that's not a dumb question. People have won Nobel Prizes for that. So there's a lot of consolidation that happens during sleep, and that's a whole different. We could almost have a meetup on that. I'm actually don't know a whole lot about it, but I know there's a lot of synapse consolidation and changing and learning occurring during sleep, like REM sleep and stuff. So people think maybe a lot of this stuff happens maybe during sleep faster. So anyway, this is something that's not modeled in machine learning. This little video, see if I can get this to play, shows this kind of happening. You can see this is a neuron and dendrites, and what you'll see is that eventually you'll see these axons that are actually growing and making connection. There's an axon coming in, so it's an output from another neuron that's coming in, and it's forming a connection. So this is what our brains are doing every day, basically, is these neurons are moving around and the outputs are changing and making connections and dropping other connections and things like that. So it's pretty impressive. Okay, so I'm wrapping up almost.
Biological. Is that biological? That's a
simulation.
Drawing,
Yeah, it's a simulation, but it's like that. It's hard to kind of do these movies in real time, but.
Are they trying to establish new connections because that neuron specifically is like firing more than?
Yeah. So it might be that. So the basic principle is this Hebbian-like principle. Like if two neurons are firing together, they will tend to wire together.
Oh.
And so this is this growth process that happens.
And how long is the growth process?
In terms of how far?
Yeah, or
in
like
distance,
how
or?
long does it take to like connect?
Oh, I don't know, but I mean, I know that, some stuff happens within a day. But some could be, there's many different timescales of learning in the neocortex, but I think this is roughly on the order of a day.
Interesting.
Okay, so wrapping up a little bit, this was a very fast tour of sparsity in neocortex. So one thing I was curious about is, when I was doing these slides, is how many ways is the neocortex sparse? So I started off with 3 different types of sparsity. So population sparsity means a small percentage of neurons are active right now. Lifetime sparsity is basically cells don't fire that often. The dynamic connections are sparse and dynamic. So these little segments are dynamically connected to a very small percentage of potential contributions. Then I mentioned sparse learning. So if you look at a neuron, only a small percentage of the cell's synapses or weights are actually updated during learning. Okay, so learning is extremely sparse. The synapse weights are sparse. If you, whereas in machine learning we might deal with 32-bit floating point numbers, the resolution, if you look at all the possible values it could take, it's a very sparse set of values. It's basically binary. So you can think of the resolution of synapses as being very, very sparse. And the last one, because of all of this stuff, the energy usage is really sparse. So only a small percentage of the neocortex is actually sort of using up significant energy at any point in time. And of course, this is changing as the neocortex is learning patterns. The exact locations are changing, but at any point in time, only a small percentage of of the energy that could be generated is actually being used up. So, yeah.
So for number 4, when you say during learning, is that learning a specific thing or over a lifetime only?
Always, basically. So whenever these pyramidal neurons are learning, it's only a very small percentage of the synapses are generally being updated. I shouldn't say always. Nothing is always in neuroscience, but a large part of the time.
Might they be concentrated on those little segments?
Yeah, exactly. So
Just one segment is being
a lot of
activated.
it's concentrated on those segments. Yeah, exactly. So wherever it recognizes sparse patterns, that's where a lot of the learning tends to occur. Okay, so I'll leave you with this since we're going to switch to machine learning. I'll leave you with this thought. So I tried to convince you that the neocortex has extremely sparse connectivity, extremely sparse activation, sparse learning, sparse weight values, and very sparse energy usage. I would say the neocortex is an existence proof that an extremely sparse dynamic system can operate more intelligently than any dense machine learning system in existence today. Okay, so we know these sort of it's possible for such a really sparse system to do very well. It's an existence proof. So the question, though, is this really required? And this is an interesting topic. I think that this type of dynamic sparsity, like the neocortex, is required for building intelligent systems. If you really want to have anything that's reasonable scale, you're going to have very efficient energy usage. You'll want to be able to continuously learn throughout your lifetime. Perhaps there's other ways, but my thesis is that this is required for building intelligent systems. So maybe that'll provoke some discussion. I don't know. Okay, thanks. Thank you. Are there questions? Who doesn't believe this? Okay. Is that too shy?
So the brain uses what, 2 watts or something?
Yeah, it's like 40 watts, I think.
40
the brain,
watts.
the entire brain.
And
Whereas
it burns up 20% of the calories in your.
yeah, but if you think about like a GPU-based system or something that's running, was it GPT-2 or some of these big NLP systems and stuff, it's just huge energy usage. So
Yeah.
nothing is as efficient as the brain.
But what if then you need as much time as evolution to find the intelligent system? That's not practical.
Well, I'm hoping that's not the case. Yeah, I think it's already there. We can study it. So hopefully we don't have to do it wait that long. Yeah.
All right, thanks, Victoria. Matt, you don't have these. Oh, this is. I'm just charging my computer. I was charging, thinking I was about to use these. So, like every computer science major, I don't know the first thing about computers. Alright, so thanks for coming. Sorry for a bit crowded place. This is our second meetup, and we started this series of meetups about brain-inspired machine learning. We started last month with continual learning, and then this month's about sparsity, and next one is about, maybe you guys can help me decide. I have no idea actually. So last time we did like a brief literature review. I'm not an expert. I was not an expert in continual learning. I'm also not an expert in sparsity. But I'm a researcher in machine learning. I went through the papers, and it contains a lot of my opinion as well in this literature review. So please feel free to stop me and disagree That's okay. We're just disagreeing outside. That's right. So the first question, maybe I shouldn't start with that, but the first question that I'm going to ask is how relevant are neural network weights? And I'm going to go through a few papers starting from Lecan, 1990s. This work was done while he was still at AT&T Bell Labs.
Hey Lucas, do me a favor, put your hand up there by the screen because the camera's out of focus. Now step right in front of it. So put your whole body in front of the camera. Okay, now step back out.
This is machine learning. There you go, machine learning.
Alright. Good. Alright. So I should say I'm not organizing this by myself, so Sam is also my co-organizer, and Matt, who is DJing outside. So just whatever the net.
Okay. Nice to see all the new people.
So the first work, it's not the first work on pruning, but it was a major work. It was done by the 1990s. And at that time it was called optimal brain damage. And the whole idea was if you remove some unimportant weights from a network, can have a network learn faster and generalize better if you remove those networks. And at the time, pruning was mainly done by magnitude, and still done by magnitude today. So Lecan proposed a slightly different approach using the second derivative. But it's fair to say that even 30 years later, we're still pruning by magnitude. So a lot of what was done at the time is sticking. This is a lot of stuff happening in between, and this is a newer work on pruning, which is referencing most of the pruning work. It's by Hand, 2015. And he was able to reduce storage and computation by an order of magnitude without affecting accuracy, just by learning which connections are important. And pruning here is mainly done on magnitude. So the approach at Hand follows like a three-step approach. He first trains the entire network, and then he prunes it, and then he retrains the entire network from scratch. He fine-tunes the network, actually. I'll try to move fast to fit into 15 minutes, so please stop me if you have some questions. And more recently, in ICLEAR, we had these two papers who made like a splash. That's Frank and Carbon, the lottery ticket hypothesis. I'm sure a lot of people in the room heard about it. And the whole idea is that dense networks contain subnetworks that, when trained in isolation, could reach a test accuracy which is comparable to the original network. So if you take a fully trained network and you prune it aggressively up to about 95% sparsity, you could achieve the same level of accuracy of the original network. So the thing is, when you over-parameterize, you're actually training a lot of small subnetworks. And the whole point is you have to find which one is going to be your lottery ticket. That's what I meant. And we have, in the same conference, we had a paper by Liu et al., 2019, Rethinking Developed Network Pruning. So Liu works with what we call structured pruning.
You know mic by any chance?
Hmm?
You know mic or something? Oh, I'm really
I don't think so. I'll speak louder or.
Oh, louder, yes, louder special.
Louder.
Louder? Okay. I'll try to speak louder. Sorry if I can. Sorry. So here he works with structured pruning. And in structured pruning, you are pruning specific parts of your structure, like an entire layer or entire channel. And the whole idea behind structured pruning is that it's easier to use it in a GPU, I would say. So if you modify your structure as opposed to what they do here, is called unstructured pruning, you just remove like random weights. It's easier to use this new network and optimize it in hardware which contains GPU. So a lot of work that has been done in structured pruning is considering that at the end of the day, you're still going to have to run on a GPU. So it doesn't matter if you just do unstructured pruning, remove a lot of connections, but you're still doing matrix-to-matrix multiplication. You're going to run on a GPU, and you won't actually get any efficiency gain if you're doing unstructured pruning. So in this work, what Liu shows is that the prune architecture is more crucial. Sorry about the text. I just did this like 2 hours ago. So what Liu finds out, he suggests pruning can be seen as a form of architectural search. And he shows that if you prune the network and you randomly reinitialize the weights, you can get to the same levels of accuracy than before. So in the work by Frank and Carbon, he's using, he resets the weights to their initial values, while in Frank and Carbon, he just randomly reinitializes the weights. and he can get the same level of accuracy. So both of these works are showing that the final weight's not that relevant as we used to think about. And so after lottery ticket, we have the work by Zhou, which is here, and Jason's here, right? Right, and Jason is there. And I'm not going to talk a lot about it, because she'll talk next. But mainly it's a follow-up on the lottery ticket hypothesis, and they show that you don't even have to reinitialize the weights to their initial values. If you just initialize to a constant, and you keep the same sign as of the original weights, that's enough for the network to have a better accuracy than the fully dense model. Is that correct? Kind of, right? So I'll move a little bit on from the pruning network. We have this very interesting paper we reviewed last week. It's called Weight Agnostic Neural Networks. And the question he asked is, to what extent neural networks alone, without learning any parameter at all, can encode solutions for a given task? And the way he approaches this problem is that he has one single shared weight for all the weights. So all the weights have the exact same value, and he does not train the network. And he's testing this network against the task. It's a reinforcement learning task. And he's using the reward as a signal for a genetic algorithm that learns how to evolve this network. So he evolves from scratch, from the minimum possible. And he gets the smaller architecture possible that without only using one shared weight is able to accomplish a task. And that's actually quite impressive that he's able to get, so in a reinforcement learning task, this data is not here, he gets about 500 total reward in a task where the dense network gets 970 and the random network gets like 50. So he gets halfway through just by learning the structure of the network through a genetic algorithm approach. It's another very recent work. That's by Zhang and Sunny Benjo at Google. And what they do is they get a fully trained convolutional neural network, and they analyze the relevance of each layer. And the way they do it is they get one layer, and they randomize or they reinitialize the weights. These results are reinitializing the weights. So they reinitialize the weights to their original value, and they evaluate if the accuracy stays the same. And what they show is that most of those weights, you can actually reinitialize, most of these layers, you can reinitialize the weights to the original values, and you still get the same accuracy. So they are not actually doing a lot of things. The ones which are actually really relevant are the ones in the beginning and at the end. And the hypothesis that it puts out in the paper is that the network learns just the amount of weights that it needs to learn. So even if it's fully over-parameterized, it falls back to the de facto number of parameters that it needs to learn whatever task it needs to learn. So if it's a small network, it's going to use all the layers. But if it's a big network for a small task, if it's over-parameterized, it's only going to learn a small percentage of the parameters, and those are the ones that actually learn. So this is a fully dense network, it's not a sparse network. The reason I'm showing here in the same context of sparsity is that just to show you that a lot of the weights in a neural network, even a fully trained one, doesn't mean almost anything. These are just random nonlinear transformations. You can change the values and you get the same results. So if the network structure is in fact important, can we also learn it during training? And we have a few hints at that question. So one of the first works that comes from the pruning community is this to prune or not to prune. I think I was discussing with someone here. And what they test is they test large sparse models with small dense models. Both have the same number of parameters. And he tries to find out which one is best. And he gets to the conclusion that large sparse is always best than small dense if they have the same number of parameters. And they consistently outperform small dense models, and they can achieve up to 10 times the reduction number of non-zero parameters with almost no loss in accuracy. We have this work by Loisius, which we also discussed here last week. It's actually in the board.
Yeah, I discussed it this morning.
Well, we discussed this morning, it's actually in the board. And it proposes a method of sparsifying the network during training as well, doing what he calls L0 regularization. The way he does it's a little bit complex. Maybe we shouldn't go into details right now, but it's a good paper on the same side. So this was heavily inspired in neuroscience as well. It's this was published in Nature. I'm sorry. And the idea behind this paper, so we're moving now from starting dense and finishing sparse to starting sparse and finishing sparse. So the idea behind this paper is that you have sparse weights from the beginning, and then during training, you learn the connections which are relevant. So you allow connections to grow, and you allow connections to decay. And the idea is that if you can find the lottery ticket during training, but being sparse all the way, what you get with that is that you can have efficiency not only for inference, but you can have efficiency at training time as well. So you can deploy this on a hardware. You can train this on a hardware which is specifically suited for sparse networks. And you can get that 20 times or 10 times again of efficiency. It's faster and more power efficient. So the way they do this is actually very simple. They just prune by magnitude every epoch, and then they randomly grow weights at every epoch. That's it. And magically it outperforms dense networks. And there's a lot of work built on top of that. That's from 2018. So we have this work by Mostaf and Wang. So Wang actually works for Cerebra, I think it says in that before. And they proposed this framework called dynamic sparse reparametrization. That's hard for me to say. And it's basically the same work that Volcano did, but they allow reallocation of 3 parameters between layers. So when they add new weights, they have a heuristic which decides which layer is more relevant, and the layer which is more relevant will get more weights. So that's the whole idea. So at the end, you can have layers which are very sparse, like the layers in the middle that are not doing anything, and the layers in the beginning. At the end, we have a lot more weights. But the overall sparsity of the network is still going to be the same. And this is even newer. We're also discussing outside. And it builds on the same idea, but it develops a better algorithm to decide which weights to prune and which weights to add. It uses a momentum. Right, I just want to cite this real quick. These are other works on sparsifying, one-time neuropruning, and deep rewiring. This is really interesting. They use reinforcement learning for it. But I won't go into details. So I'll just have that. Okay, so what else can we gain from sparsity? One of the things we're looking at here is continual learning. That was the theme of our last meetup. And the whole idea is that if you have sparse neural networks, you have a lot of extra capacity in that network that you could use to learn other tasks. You could use to learn newer tasks. So this is one of the methods that aims, that has this approach. It's called continual learning via neuropruning, and the whole idea is that if you can prune your network and you can have paths in the network which are unaffected by other paths, so if you learn a specific path and that path is completely orthogonal to a different path, you can have the same network learning several different concepts at the same time without interfering with one another. So it's a little bit like elastic weight consolidation, but the thing behind elastic weight consolidation is that you have a restriction on some parameters, but you're still modifying them a little bit. So you have concepts which are, when you learn a new concept, you change the other one a little bit. So with pruning, you can have completely independent concepts. So this is one of the things that Sparsity could be useful for. The other thing is Subutai's paper, is he just presented. Subutai and Luis, which is there, right there. And the idea behind this paper, also what they show, and I think they said, is that sparse connections has another property which is really interesting, that they are naturally robust to noise. And this graph shows sparse networks compared to dense networks. And as you add noise to your input, sparse networks are naturally more robust to it without doing anything else. So this paper will have sparsity not only in the connections. So I have been talking about sparsity in connections all along. It also has sparsity in the activation function. So the activation function is a key-winners function, which basically implements the value with a moving threshold. And that leads to a very sparse activation as well. So we have 20% sparsity in weights and 20% sparsity in activations. We actually have 4% sparsity in there, which is really sparse. And can it train faster? So maybe in GPUs. So we have this paper we discussed 2 weeks ago. It's an open AI GPU kernel to block sparse rates. And what they do is they apply sparsity, but they apply sparsity in a way that you could optimize for GPUs, so apply it in blocks instead of completely unstructured pruning. But we can also try better approaches. So these guys are here.
Hey.
I'm not going to say a lot about it, so you can, I'm not going to go over it. We have other terms as well. Sorry, but I needed to mention, so this is just about hardware, right? And Survivor is also talking about being a hardware specific for sparse neural networks. And this is like a huge chip. I don't know how they do that. It's a very big chip for a very small person. All right, that's it. Thank you. It's you. No one asked any question or anything, so I don't know if I'm worried or not. Oh, sorry.
So in starting the presentation, we were discussing about like how when they're starting to retrain network, like some of them froze the initial way, some of them randomized it, and some of them kept as zero initialization. And then a couple of slides down, the team at Google that trained the full convolutional neural network, they were inferring that only the initial layers and the final layers mattered. But if we put these two results together, do you have any comments about it? Because from one type of result, it seems like initial layers don't matter a lot. Maybe I'm wrong with that. And by the inference from Google, it seems like initial and the final layers are the ones that matter the most.
I think you didn't get the whole question, so what did you say in the beginning?
Yeah, like so I was saying in the initial part of the presentation, we were telling about how when they train the network completely and then they keep the initial layer as constant, or they make it zero, or they.
Oh, okay. Okay.
Yeah.
So the prune work, you're not like pruning entire layers, and most of the work I talk about is pruning, is unstructured pruning, so you're pruning networks, neurons along your network. It's not like you're removing a specific layer out of networks. And Google's work, that's just a dense network they train. That's not sparse at all, it's just a dense network. And they analyze the results of the dense network. So those are, two different. So the sparse is you're not like sparsifying by removing an entire layer, you're sparsifying by removing neurons or just specific channels or a I kept it short because today we have a lot of great presentations. I mean, you don't want to. There's one chart there. Someone wants to do
Okay. Yes, please. You're so prepared.
I know. You gotta plug this in.
Alright, hi guys. I'm Hattie. Glad to be here. Thanks, Lucas, for inviting me. So today I will be talking about the paper that Lucas mentioned earlier called Deconstructing Lottery Tickets. It's done with other folks at Uber AI Labs, including Jason, who's sitting there. So this work is building on the idea of neural network pruning and the lottery ticket hypothesis. And as we know, neural network pruning is a popular way of reducing the size of neural networks. And it typically follows a standard procedure. First, you train the network to convergence as you would normally. And then you want to remove superfluous structure from the network. So in this work, we consider the type of pruning that's magnitude-based sparse pruning or unstructured pruning, meaning removing individual weights. But once you remove the weights, you've damage the function that the network has learned, so you need to fine-tune the network some more. So how well does this work? Well, as Lucas mentioned, in Han and L, they show that you can actually get networks that are 10 times smaller with no drop in accuracy. So if pruning works so well, why don't we just train a prune network from the start? The answer, of course, is that it doesn't work. If you randomly reinitialize the weights and you train a prune network, it does not reach the same accuracy. So recently, this paper by Frankel and Carbon called the lottery ticket hypothesis showed that you can actually train a prune network from scratch, but only if you maintain the same original initialization for the prune weights. So they proposed a variant of the pruning algorithm, which I'll call the lottery ticket algorithm. So first you randomly initialize the network, and then you train it to convergence, and you prune weights that have the smallest final magnitudes. So up to this point, it's the same as what we talked about before. But they do this special step, which rewinds the remaining weights back to their original initialization values. And then they train the network from this point. So we do it in an iterative fashion, repeating steps 2 to 4 iteratively and removing an additional percentage of the network each time. So using this procedure, they showed some interesting results. Here the y-axis shows test accuracy of the networks, and the x-axis shows the level of pruning, which is basically the percentage of weights remaining. And here we'll look at a convolutional network trained on C410. The black line represents the original accuracy of that network without any pruning. So as we move from the left side to the right side of the x-axis, we prune the network more and more, and we see that the prune networks actually perform even better than the original network. And if we continue to prune, the performance drops back down to match the original full network. But at this point, we've aggressively pruned the network, so we have about 5% of the weights remaining.
So, is the input or what you train on that data exactly the same every time? Or is it a different sample of the stuff? I mean, in other words, is the pruning getting rid of the noise and focusing on the what's not noise, and then you overlearn basically? I mean, that's what it seems like.
So the data is the same set of data. The order that the network sees in might differ, but it's the same set of data. It's the network sees it over and over again during training.
Is it better to randomize? If it's not in the same order, is it the same data? I mean, isn't there, time doesn't matter in this? Maybe it does, maybe it doesn't, I suppose it depends.
It might matter, but so this is, the band that you see is over 5, max over 5 different runs. So each of those would have different orders. So it's the phenomena is relatively consistent. So I think it's probably pretty robust to data ordering noise. Yeah, so if we continue to prune, the performance drops more, as you might expect. However, this level of performance is only true when you rewind the weights back to its initial values. If you randomly reinitialize the weights before retraining, then the performance is much worse. So, based on these results, they proposed the lottery ticket hypothesis that randomly initialized dense neural networks contain subnetworks that's initialized such that when trained in isolation can match the performance of the original network. They call these subnetworks winning tickets and suggested that it's a combination of their initialization and structure that makes their training particularly effective.
I'm kind of surprised that performance drop is so steep in that
Here?
with the yellow curve.
Here?
That even if you have like 90, it's not a, it's a long
Yeah.
scale. Okay.
Yeah. Right. So, but yeah, it is quite a
steep,
gap.
Well, I've seen other papers that they were talking about this steep on the blue curve, that there's a sparsity level that when you go below that, it suddenly drops like pretty fast.
Mhm.
So you get to a point that you have the optimal number of parameters, and if you just go a bit below, then you're just introducing a lot of bias.
Yeah.
So I've seen that in like many printing papers, that curve.
Yeah. We've had runs that basically goes like that.
Right.
So, you don't see that here, but
Quick question.
Yeah.
Do you have any idea as to why theoretically you get that increase in accuracy from about 0% sparsity to whatever that is,
This part?
90? Yeah.
well, that's a very good question.
Yeah.
So some of the later stuff I'll show might hint at why that is, but I don't think we have a formal explanation. Definitely not a theoretical explanation.
And is that increase a general thing you see across a lot of data sets?
So we only, us and the original lottery ticket paper only looked at C410 and MNIST.
Mm-hmm.
I think there are new work that show you don't really see this on, say, ImageNet. And what you actually need on ImageNet is, instead of rewinding to original initialization, you rewind back to some value at, say, epoch 1.
Oh, okay.
Which isn't really consistent with their hypothesis, but that's, yeah.
I have a question real fast.
Yeah.
Is this only for CNNs, and are you pruning only the filters, or are you pruning the final layer as well? Final fully connected layer?
Yeah, so this example is a CNN. We also have FC, and we're printing each layer.
So the
Conv
convolution
and FC, yeah.
Even the very first layer?
Yeah.
Okay.
Especially the first, but
especially
the last,
Especially the
well,
first
not
layer.
especially.
Yeah, because the
but-
very first one has a very tiny number of weights, the first filter.
Yeah, so
That's
the conv layers are pruned less than the fully connected layers. And we prune the last layer less also. So the last layer is pretty, it needs to be less sparse, basically. Needs to be
Is
more
that a
dense.
choice, or is it because of the metric? Like, is it just more important, or is it out of a choice that you make that you don't feel enough?
It works better when you,
I think it's because normally in your classification layer, you're going from however many neurons in the layer before that to maybe just 10, right? If you're SciFar MNIST, you only have 10 labels. So if you're using 95% sparsity, you only have, I don't know what the math is, but a very small number of parameters. So if you're doing if you only have 50 parameters for that final classification, normally it's just too few.
Yeah, the last layer is pretty small. Yeah, it's tied to the output class. Cool. So, right, so we wanted to study that effect that they proposed by basically studying the 3 important components of their algorithm. So the mask 0 action means basically, so the way you do pruning is you multiply weights by a mask of 1s and 0s. And when you multiply by 0, that means you're pruning the weight. And this is referring to what we do to the weights that are pruned. And then we have the mask criteria, which is how we determine which weights are not important. And we also have the mask 1 action, which is what we do to the weights that we keep. So, starting from the first one, motivating question here is, does the value that we set the prune weights to matter for the accuracy of the network? And before answering this question, I want to take a little detour to tell you about a strange phenomenon we observed while training these networks. And I promise that it will become relevant to that question later. So imagine you initialize a network randomly, and you apply it on the MNIST data set. Without training the network, how well do you think it would do? Well, if you don't train the network, you would expect no better than chance performance, which in this case about 10%. Similarly, if you apply a random mask to this network, you would still just expect chance performance. However, if you apply a mask derived from the lottery ticket algorithm on this network, without training the weights, you actually get a network that performs significantly better than chance. So this may be surprising since the only thing we're doing is removing certain weights from the network, from a randomly initialized network. So we call masks with this property that they generate partially working networks without training the underlying weights super masks. So that's why that's in our title. So why do these super masks exist? Well, it turns out by answering our first question, we can also provide an explanation for them. So the pruning procedure performs two actions. It sets the prune weights to 0, and then freezes them during retraining. We can decouple the effects of these two actions by running a simple experiment. So instead of setting the prune weights to 0, we can freeze them at their randomly initialized values. If the value of the prune weights don't matter, then this should perform similarly well. However, we see that that's not the case. So if we set the prune weights to their initial values, the performance is significantly worse. So this seems to suggest that the value of the prune weights do contribute to the overall performance of the prune networks. And it seems that 0 is a particularly good value for them. So to see why that might be, we need to take a closer look at the mask criteria we're using. We can think of different mask criteria as regions on a 2D plane, with the x-axis being the value of the initial weights and y being the value of the final weights. This ellipse represents a distribution of weights from a given layer. It's tilted because the initial values tend to correlate with the final values. So the mask criteria used in the lottery ticket algorithm keeps weights with the largest final magnitudes, regardless of what their initial values are. We refer to this as large final. So it sets weights with the smallest magnitudes to 0. So what this is actually doing is setting to 0 weights that end up closest to 0 at the end of the training process. So this leads us to propose the hypothesis that masking is training. The masking operation tends to move weights in the direction they would have moved during training. So this provides a potential explanation for super masks, since with a well-chosen mask, you're setting a subset of the network towards its final values. To test this hypothesis, we can run a second experiment. For any weight to be pruned, we set it to 0 only if it moved towards 0 over the course of training, and we freeze it at its initial values otherwise. Using this treatment, we get networks that perform just as well as the lottery ticket networks, even though we did not set all of the prune weights to 0. In fact, if we apply this treatment to all the weights, including the weights we keep, that is, if the weight decrease in magnitude, we'll initialize it at 0 in the next round, we get networks that can perform even better than the lottery ticket networks. So these results support our hypothesis, and it suggests that thinking of masking as training may be a valuable perspective. And so here is just the same thing on 4 different networks. Basically, we see similar patterns, except for in a fully connected network, everything seems to work. But it's also on MNIST. Okay, so now that we explored the first part, let's look at the mask criteria we're using. So are there other ways to basically select which weights we keep? Or is this phenomenon unique to the large final mask criteria? Given our view on masking as training, an obvious thing we can try is, instead of keeping weights with the largest final magnitudes, we can keep weights that increase in magnitude the most during training. So that's illustrated here, call it magnitude increase. And this mask criteria would basically explicitly set weights to 0, then move most towards 0 during training. So does this work? Well, luckily, yes, as we might expect. So that's the green line compared to the original large final criteria. So this works and sometimes works significantly better than large final. In the paper, we also tried a bunch of different mask criteria, not all of which we expect to work, but we wanted to check our understanding. For the sake of time, I won't really go through all of them, but we see some criteria that can produce walkthrough tickets in that they can match or exceed the performance of the original network, and a bunch that don't. Yeah, similarly, we have the same thing on the 4 different networks, and the thing to note are the stars, which basically show printing iterations where magnitude increase is significantly better than large final. Alright, so moving on to mask 1 action. So the lottery ticket hypothesis paper showed that you have to rewind the weights back to their initial values. But do you have to keep the exact values? The weight's initial value has 2 components, the magnitude and the sign. Is it the combination of the 2 that we must maintain, or is one of them enough? Coming back to this plot, you remember this is when you reinitialize the weights randomly. So to see which component is important, we can try a variant of this where we reinitialize the weights, but then after that, force the weights to have the same sign as their original initialization. And that's shown by the solid yellow line here. And the black line is a baseline, which is random pruning, meaning you apply a random mask to prune the network. So we see that if we keep the sign the same, we get a big increase in performance over the reinit experiment, but still not quite to the lottery ticket performance. So another thing you might think is that since we know that initial values tend to correlate with final values, and we're keeping weights with large final values, then the initial values of the kept weights may not have the same distribution as the overall network. And that's illustrated here, so the blue represents the distribution of the kept weights initial values. So perhaps if we followed this distribution to reinitialize the weights, that could work better. And the way we do it is basically shuffling the values in here randomly. So that also does not work. And that's shown by the dashed line here. Sometimes it gets pretty unstable as well. However, if we maintain the sign, we see that the network works much better, and it gets pretty close to the blue line. So it seems like the sign, yeah, see, there's a pattern here. So the sign seems to be the most important thing to maintain. So in fact, we can actually initialize all the weights to a constant value, and as long as we keep the sign the same, we get networks that work just as well as the original lottery ticket network. So this really shows that the relative magnitude of the weights don't matter at all. It seems that the sign is the most important component here. Yeah, so you see a similar pattern in all the networks we tried. Okay, so we can ask one last question. If we think of masking as training, what if that's the only training procedure we perform? How well can we do then? Earlier I showed that using the large final mask, on MNIST we can get accuracy close to 40%. But can we do better than this? What if instead of keeping weights with large final magnitudes, we keep the large final weights only if they maintain the same sign by the end of training. So here is like the difference between the two. And this gives us a network whose initial values have the correct sign, or the sign that they would have had at the end of training. So using this simple criteria, we get pretty remarkable results. If we multiply this mask on untrained weights, we get close to 80% on MNIST and up to 24% on CPR10. Interestingly, if we converted all the weights to constant value, similar to the mask 1 experiments, we get networks that work even better, up to 86% on MNIST and 41% on CPR. So this network, basically, all the values here are either 0 or a plus minus constant value. And we also wanted to see if we can push the performance of this by learning a mask directly. So we're using gradient descent to learn a mask on the randomly initialized weights. And here we're looking at basically a learned mask multiplied by the same sign constant from here. And now we're seeing results that are closer to what a fully trained network might see. If we do some more tricks, then we get even better results, which is, in this case, very similar to a fully trained network. But here we're not training the underlying weights at all.
I think it is step. How do you learn the mask?
Check out a paper.
Alright. That's more like, I was hoping to get that.
Well, basically, the masks, we use a Bernoulli sampler so what you're learning is like the probability for each weight to have a corresponding mask with 0 or 1.
They don't have reparameterization trick.
Well,
It is kind of.
that's the other paper you got?
Yeah, the
I'm
zero
not
regular.
familiar with that.
Alright.
That's
I think
like
it's the same
Bayesian.
idea.
That's like a Bayesian.
Yeah.
It's common.
It's the same idea.
You're using this.
Okay.
So you learn the probability of that weight being active or not, or being 1 or 0.
Right.
I want to point out a really interesting correlation between this result and the neuroscience stuff I presented. I didn't present one thing there, but learning the mask is basically learning the structure. You're either dropping or adding connections, and that's one of the main forms of learning that happens in neocortex. The actual weight value, as I mentioned, is almost non-existent. It's almost like mind rate, which is very close to the. And the thing about keeping the sign the same. I didn't cover this, but synapses in neocortex are either positive or inhibitory, excitatory, inhibitory. They never split signs.
Oh, that's interesting.
So it's almost an exact match to these.
Wow.
It's kind of cool.
That's really interesting, because you might wonder, like, I mean, these masks, they depend on the ways that they're learned on.
Yeah.
But some, you can wonder if you can get masks that don't depend on the ways.
Right.
But it seems like the brain doesn't do that.
Yeah, brain. Let's figure out some other way to learn
That's
masks.
really
This is pretty much a trinary.
Yeah. Yeah. We do have a different value for the constant for each layer,
Oh,
but probably you can find one. Actually, I think I tried to use just 0.1 and it works. so it's not super sensitive.
How sparse are these masks?
Good question. I think, I don't remember exactly, because, so these are basically the values from the max performing sparsity, but I think probably less than 50%.
But I think they were like all somewhere near 50%, not so far away from 50. It can't be like 2 close to 100 or 2 close to 0 because there's no information in the mask then. So I think they were all what?
But
40,
in the
60 or something.
Yeah, something like that.
in the graphs you showed that the peak was at around 26% of
The graph
active weight.
at the beginning?
Yeah, like all the graphs you have performance, you have like sparse on the x-axis, and they all seem to have a peak at around 26% of active
I
weight.
have this thing here. Which
Yeah, that.
Oh, you know this graph? Okay, so this is just showing supermask performance. As in, so all these are untrained underlying weights. And it seems like, and this orange corresponds to that large triangle same sign mass criteria. So it seems like there's some sweet spot.
Like around 15%, right? Like 16%.
Yeah, although I think the lure masks are a little less sparse. Actually, so the red line represents the lure mask, so you can see where it is. This is I think this column. So yeah, close to 50. So actually, we can't directly control the sparsity when we learn the mass. So that's we couldn't like complete this plot. Well, yeah, that's all. Thanks for listening. Also, you can check out this blog for more discussion.
But my question is, when you deploy to production, and what kind of application are you using?
Yeah, so
none.
Well, if you have any ideas for how Uber could use this, right now it's not for any like application reasons. I mean, yeah, I don't know. Maybe Sparsity might have some applications, but yeah.
Do your networks have batch norm always? Like, is some form of norm? Did you try to remove the normalization and see if
Yeah, there are no batch norm in
Oh, there's no batch.
Yeah,
The
no.
actual adjustments within
Does this suggest that if you pick which weights to keep instead of what all the weights should be, it works pretty much as well? At least on these sets, so there's a lot of computers wasting a lot of energy.
You mean?
I mean, when you show those last two columns,
Here?
like, okay, like, right, exactly. So like when you, because normally if there's like in a normal situation, or not normal, in a situation where you don't have a mask, you're changing all the weights. But it seems like you put on this mask, and then like it works essentially as well by just choosing. So is there then not backprop involved anymore? If you're learning what the mask is that sort of instead of learning what all the weights are, so just replace
So
that?
the mass is learned through backprop.
Okay, the mask is learned through backprop.
Yeah,
Okay.
but the weights don't change, which is maybe an interesting take on the lottery ticket hypothesis, because you can think of this, the thing that the learn mass uncovers as a subnetwork within a randomly initialized network that already works well.
Yeah. Right, that has been mentioned too.
Right.
So this is sign constant per layer. Each layer has a different constant.
Yeah. So the constant we're using is the standard deviation of the layer's initial values. It's pretty simple heuristic. But in this one, we're doing something like where we scale the sign constant based on the sparsity level at each iteration. And that gives us a pretty big boost in performance, which is interesting. Not sure why that would be. Cool. Alright.
Thank you.
Alright, let's go.
Let's do a 5 minutes break before Wadi set up.
Sure.
So people can go to the bathroom now.
Alright.
Glad you.
Yeah, a little break. Toasting.
So expensive. I think we're running a little over time.
Yeah.
That's
what
All right,
Yeah.
I can do that. I can try. I'll skip through the high level stuff. You know.
Before going to the diagram now, maybe
They'll be a little refreshed.
Yeah.
A little refreshed. Quicker.
Did you have any thoughts between the difference, like the 60 to 40% sparsity versus the 0.5 to 2% in general networks? Like, what was going on in your head?
Yeah, this is still much denser than what's in the deploy the Neocortex.
Yeah. Because it's still point neuron. It's still point neuron network.
It's still
yeah, that's it. I was like, well, this is maybe as much as you can eke out. If that's
maybe.
I
mean, the lottery ticket and some of these other projects.
Yeah, we do that.
You can get that to something like 5%.
As a trend. I mean, you guess as a trend network.
Yeah, we don't have to write learning algorithms yet for.
Less. So.
Yeah, I think with active dendrites,
a lot less.
Very sparse, yeah.
So you need a network structure.
Yeah.
So is it located here or there?
We're just down the street. Actually, we can walk 5 minutes away. There's a little USB
I think there was a
guide
USB,
for this. Is there the USB for the clicker? I think that, oh, that's right there. Okay. Thanks so much.
Oh, that's easy.
That was a ball?
It's funny how we've all just got used to carrying all these dongles.
Right. The amount of like offset that didn't have USB-C.
Yeah.
Do you have any analogy to the large final weight change in neuroscience? Is there any similarity?
So that was large final weight. What was the exact?
Yeah, it was
there?
like it is like the masks were the masks that had larger final weights were performing more. So, but if I'm not wrong,
So you're presenting?
the masks here basically
Go
instructions
for it.
of
It's all yours.
Exactly. Yeah. Yeah.
Almost like what
I was sitting there. You go steal.
Sorry.
which parameters
I
actually?
was sitting like right here.
Right.
Like, oh, which have changed?
Yeah.
You know,
Yeah.
because it's like there's so many parameters, but it's like, how do we know we need all these parameters? We don't.
Yeah.
As opposed to something like HCM where you start at 0 and learn how to bring parameters.
Right.
Yeah, so it's like, it seems like the thing is like, yeah, we don't need all these parameters.
Yeah.
You know, like,
Yeah.
and random is the thing when you read it. So that's
Yeah. Yeah. So,
smart.
right. Yeah, it makes sense. Yeah. So in neuroscience, it's like which neurons have like higher action potential above the threshold. So they.
Which small subset is relevant right now, as opposed to what does everybody think all the time?
And this will
Yeah, well, so one
change.
thing her networks don't have is the activity is not sparse. It's only the connection that's sparse.
Correct.
The brain activity is also sparse.
Right.
So it's sparse kind of sparse.
Right.
So I think that introduces a twist.
Right. Yeah, and if I'm not wrong, it's like parts of brain have different activities. Like there is one for speech versus one for like playing cricket or something.
Yeah.
Okay.
Yeah.
Okay.
It's like different parts of the neocortex map.
Well, and it's not actually
Or we can bring Jack. I would wait for that. He said it's 1,000.
Yeah.
Right.
Okay.
That's always a good sign.
I usurped. No, we're
So yeah, as we all get seated, just a little preface. This is probably a little more, it will start pretty high level, so in the interest of time, I will not spend too much time like on all the very high level motivation stuff, but typically give this presentation to a broad range of audiences. Y'all are probably some of the more technical ones. So, but hopefully it'll be, for the beginning will be a little bit of a refresher on like GPUs and CPUs, and there's a little bit of history of AI. So it's a fun presentation I like to give, but we'll definitely dive into the meat of it too. And since everyone's seated, I'll just get started. All right, I'm Gorden Wilson. I'm the CEO and co-founder of Rain Neuromorphics. We are just down the street, about a 5-minute walk, and we have a few of our folks, Jack, our CTO, Ross, our first employee, Nikita, Alex, Anuraj, and Ilya, who all came over and walked over to join for this meeting today. So we build processors for artificial intelligence that are inspired by the brain. And also, just a little fun fact, one of the books that Jack read 5 years ago was on intelligence, or more than 5 years ago now, which was one of his core inspirations to invent this technology. But we'll get right to it. So our mission is to build the first hardware that can power brain scale intelligence. So we'll talk a lot about scaling of neural compute, and basically how the existing paradigms scale, and what are the limitations to that, and how we are seeking to improve upon that by kind of fundamentally rethinking the core processing underneath neural networks. So we'll skip through this a little bit, but we're founders, and I know it's an intimidating number of slides, but it moves quickly. So we're from Florida, Gainesville, Florida. We moved out here a year ago. On our board, we have the guy who commercialized GPS chips. He's a cool, legit guy. Some of our investors, our biggest investor is the CEO of OpenAI. We did Y Combinator last summer, Sam Altman, as well as some folks like Scott Gray, who wrote that block sparse paper. And our key partners we work with are TSMC and OpenAI right now. Nice. So this is a long presentation. I'll probably not do number 6, but we'll certainly go through the first 5, kind of giving a history, kind of the motivations behind needing to have a fundamental paradigm shift in scaling neural compute, and then talk about our hardware and how sparsity is really kind of the core concept that underlies the motivations of our hardware and why it works. So the first part we'll go through quickly, but AI and its hardware and intertwined history. The first AI hardware, which you may or may not have known, was called the Mark I Perceptron, and it was built by Frank Rosenblatt in 1958. And it looked like this. It was this, right? This wild mesh of wires, right? That were 400 of these like optical inputs that were actually randomly connected to another layer of neurons. But it was only a single layer of neurons, and as Marvin Minsky then wrote a few years later in his book Perceptrons, and kind of crapped all over it, it was not very capable of what it could do, even though the New York Times was like, it's going to go to space and take over the world and become conscious. So it did not become conscious, spoiler alert. But over the course of the last 60 years, we've seen these ebbs and flows of AI summers and winters. But one thing that we see across the board is that there was really kind of fundamentally defined by the computing power that people had available at the time. People always had really powerful imaginations and were creative in thinking about the algorithms that we could create, but they were limited in the hardware they had running it. So the first summer was from 56 to 74. It was marked by this kind of untethered, undirected funding from the government, the US and the UK, that ended for our first winter until 1980. And notably, the NLP model that was made during the first summer, it had the maximum vocabulary it could support was 20 words, because the best computer just ran out of memory, right? And Hans Moravec, during that winter, had said that we needed about 1 million times better computers. And funny enough, if you track Moore's law scaling, we're like right there at the 1 million times right now. So the second summer was 1980 to 1987. This was the Japanese 5th generation computing project, getting really motivated by this imagination around robotics. Again, a lot of excitement, and it even led to this kind of industry around expert systems that we saw rise in the 80s. But like 300 companies kind of went defunct. This billion-dollar industry of AI didn't really emerge as people thought it would, and that led to our second winter until 1993. But from there, we saw really Moore's law scaling pick up. And the benefit of Moore's law meant that people could build rules-based AI systems that really started to capture people's imaginations of what we could actually now do. So this was when when the DARPA Grand Challenge was won for the first time, with Stanford robot, when IBM Watson was on Jeopardy, those types of things. And of course, when we get to 2012, we're in the GPU revolution. That's where we are today, and that's what the modern deep learning has all been defined around, the onset of using GPUs to parallelize neural networks. So of course, what's next? So part 2, we'll talk about AI silicon today, like what are we using and why? is this the de facto hardware for training and inference on neural networks? So you probably don't need me to tell you, but it's these guys. This is the NVIDIA campus down in Santa Clara. Kind of looks like a spaceship, but they've done really well for themselves, kind of turning themselves into the deep learning company. And if you buy something from NVIDIA today, it looks like this. This is a V100 GPU. This is the top of the line GPU for training networks in a data center. Costs about $10,000, and you're using it to run neural networks. We all know what that is. So, but if we go back 14 years, so when I was actually a customer of NVIDIA when I was 14, we were buying this. This is the GeForce 360. And we weren't using it to run deep neural networks, we were using it to render graphics. Right? This was, Age of Empires, a little fuzzy here, probably needed a better GPU. But really, like when I plugged this into the PCIe slot in my tower, all of a sudden the graphics are rendering super well and super high resolution. And this is why. Because the math underneath those two things was the same. And the architecture between 2005 and 2019 also just hasn't really changed very much. It's being used to perform matrix multiplication. This is the core mathematical operation that underlies all deep neural networks. So whether you're looking at graphics, in the case of that, your matrix can correspond to pixels or polygons, and you can modify it by some type of transformation. Or if it's in a neural network, your matrix corresponds to the weights, right? And that vector is the activations moving from one layer to the next. But in both cases, this is lots and lots of small computations that need to be parallelized. And we'll get into the kind of what those architectures look like and how they scale in a second. But of course, in 2012, what really led and kicked off the GPU revolution, in 2012, it was not the first time anyone had used a GPU to train a neural network. But what it was the first time someone used multiple GPUs to divide the training and use that to parallelize and speed up the training of the neural networks so you have a larger model. This was AlexNet, and this broke the benchmark by 11%. So this really kind of kicked off the renaissance for deep learning that we're in today. And since then, the amount of compute that we're throwing at these models is just increasing like crazy. So this is a chart that came from OpenAI, and this was from their AI and compute blog post, I think at the end of in 2018. What we see from AlexNet in 2012 to AlphaGo 0 over the course of these 7 years, it was a 300,000x increase in the amount of compute required by these models. That is a doubling period of every 3.5 months. It's wild how quickly these models are growing. And fundamentally, it's about just bigger models with more neurons, more parameters that need more data, more math. And incrementally improving hardware just really can't keep up, because even though we can support these models, the number of GPUs that we're using to train these guys is orders of magnitude more than the number of GPUs we took to train things like AlexNet. So even if we can train it, we can't like deploy it practically in anywhere we want to put it. And something also to emphasize is this bitter lesson around AI compute. So the summary of this is that while variations in architecture can incrementally improve model performance, it seems if you just throw more compute at a model, make the model bigger, it seems to perform better across the board. The exact quote from Rich Sutton, who's the father of reinforcement learning, and DeepMind opened up a campus in Edmonton just for him. But they say the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective by a large margin. So we want more neural compute. So the summary of this part, I realize I need to eliminate that because I took out this slide, but the market's going to be big. Wow. Okay. NVIDIA is the current winner because they built a processor for matrix multiplication that was originally intended for graphics, and they could very easily then just become the deep learning company. And the compute needed for these most complex models is doubling every 3.5 months, and the bitter lesson seems to be that just more compute wins over creative architecture. So part 3 is a little bit of AI's bleeding edge and what lies ahead. This might be also a little bit of a review to a particular all you folks who are in the machine learning world, but bear with me. So we're seeing every month these incredible advancements in artificial neural networks. I think the 3 areas that we're most excited about at RAIN are generative models. You know, this definitely captured people's imagination in the last few months with FaceApp. Wild how well it could age us. But there's all types of deepfakes and things that are interesting and potentially socially problematic. But there are a lot of other interesting use cases of this, like companies using it to generate and imagine new drugs, imagine new proteins based on observing many types of protein structures. that are effective at fighting a disease. So an incredibly promising domain. Of course, reinforcement learning. This captured the world's imagination with AlphaGo. But I just spoke with someone from Google Brain who was saying that, and I need to find the paper because I should, but in any case, they were saying that pick and pack arms had increased in accuracy. There was a team that increased from 60 to 90% in the last year. So from these reinforcement learning models are beginning to get really good. And of course, natural language processing. So this is the transformer models, BERT, GPT-2. It's really amazing to see what these models are capable of doing right now, both in terms of in generative manners as well as just kind of question answering. But these are some of the biggest models that we have seen. And the issue is that these models can't be deployed at scale because they are so massive. And what Pete Gorden at Google Brain said is the single most important message I want to get across is there are a lot of new applications that are blocked from launching because we don't have enough computing power. So let's take a look at just how far away in scale we really are. So we say that these problems exist because hardware is neither scalable nor efficient, the hardware that exists today. And so if we look at BERT, this is one of these NLP transformer-based models. We have about 1.4 million neurons, about 110 million parameters or synapses. It's taking 1,500 kilowatt hours to train. Our brain is 86 billion neurons, or more about 500 trillion synapses, and 20 to 40 watts of power. So we are 5 orders of magnitude away in scale and energy efficiency. That is a massive, massive distance that we need to traverse if we're ever going to build really autonomous brains, right? So another emphasis that we make, and this is a little bit disjointed, I'll be cleaning this up, but essentially neural networks today are deep. We have very deep learning with neural networks, but they are not wide, right? And we believe this is fundamentally because they've been built on GPUs, and GPUs handle dense matrix multiplication really well. They do it really cheaply, and so people want to build networks that are optimized for the hardware they're running it on. So we have lots of deep, dense neural networks, but not very wide or sparse neural networks. And width enables many things. Capacity is one of them. But most obviously enables capacity in a neural network by having a higher input space. You can have many more dimensions of input that you put into that first layer. You can have, but in addition to that, width enables activation. Sparsity with, as the New Hampshire paper can, width plus sparsity can enable robustness to noise. So we're really excited about exploring width, and we want to make width cheap for researchers and deep learning engineers to explore and uncover what it can do. But fundamentally, we believe that the future of neural networks must be wide and sparse as opposed to narrow and dense in order for us to fully realize its potential. Okay. So part 4, we'll talk about the scaling challenges. So now that we know it's all matrix multiplication, we know why NVIDIA is the current winner, let's look at what it will take for us to go from the hardware we have today to anywhere close to the brain. There are 5 orders of magnitude improvement on energy and scale. Can we do it? So this will be a bit of a maybe obvious thing for some folks, but I put this together so I could very obviously explain how matrix multiplication is being used for layer transformations, so bear with me. But we have activations in neurons that correspond to this vector, and then we have weights in a matrix. The thickness corresponds to the intensity of the weight. Maybe fewer transitions is good. But in any case, and then this is now the math that defines the movement of information from this layer to the next layer, and of course this is where you have the multiply and the accumulate, right? So whenever we're at all these hardware conferences and people are throwing jargon at us, so it's like we're making math units, multiply accumulate units, because they're doing this math, right? So whoever can optimize this math really well is probably is going to be someone who can support better, more powerful neural networks. But there are really 2 ways, fundamentally, if we're looking at the core compute primitives. There are 2 ways to multiply matrix on a computer. You have digital floating point logic of varying degrees of precision, but you also have analog physics. You can perform matrix multiplication using voltages, resistances, and currents. And there's another company that's down the street over there called Mythic that's commercializing just that, as well as us. So when we look at digital logic and utilizing GPUs and digital floating point logic, the fundamental issue that it faces is that they scale poorly with time. So for two broad reasons: data movement and the von Neumann bottleneck, and order and squared scaling of matrix multiplication. So when we say data movement and the von Neumann bottleneck, we're referring to the fundamental architecture that underlies like all computers today. Right? The von Neumann architecture has a processor, a memory unit, and a serial bus that connects the two. So if you're going to do a matrix multiplication, this is a CPU, would have like one processor. It would be lots and lots of little calculations moving back and forth and back and forth and back and forth. So you can see intuitively why it would take a long time. A GPU breaks up the processor into many pieces, has many little processing units, so you can perform the math in parallel and do it a lot faster. The funny thing is, even with GPUs, something between 95 and 99% of the time, we're really reserving for just moving data, right? So many companies today in our space talk about solving the data movement problem. And when we say order and squared scaling of matrix multiplication, we're really referring to a fully connected matrix. That as you increase the size of your layer, that matrix full of dense connections is going to increase as a square. So you have a quadratic number of operations in order to move from one layer to the next. And this is why we don't see very, very wide layers in this fully connected paradigm, because they just take so many operations which just take you way too much time. So we have this other way of doing matrix multiplication, not using digital logic, but using physics, using voltages and resistances. And so what most of these architectures look like is like this. You have neurons, if you will, like these little compute elements that are on two edges of the chip that can write voltages or read currents. And they're typically, like, these could be your inputs, these could be your outputs. And then you have a grid of lines at which every cross point you have some type of resistor. You could put a flash transistor. You could put resistive RAM, DC RAM. You could even do this actually in light and photonics, and do this kind of thing. There are two companies that are doing that, or two or three. But fundamentally, these cross points carry a resistance, and so you just load up voltages, release them in a single step. They kind of run down those lines, and as those voltages cross those resistances, you have Ohm's law happening, and you can sum up the currents on the horizontal lines, and now you have matrix multiplication happening in a single computational step. So that's a crossbar array. So to again emphasize the time scaling that we see here, if we have a CPU, we're going to have, in one clock cycle, we'll be able to do one mathematical operation. If GPU is parallelized across 3 cores, it would be 3 clock cycles, or it would be able to do 3 pieces of math in one clock cycle. And with the crossbar, in one step, you can do all that math. So this would be 9 clock cycles, this would be 3, this would be 1. Of course, you also have to load up the voltages, which makes that end up being order n. But in any case, we see how the crossbar is fundamentally really fast to do this matrix multiplication. So, because of that, we see this really powerful time scaling with analog matrix multiplication. And that would suggest that analog might be really the right way to scale up, because you can avoid the time scaling issue of having to perform each of those calculations in floating point logic. But of course, there's a catch. So what is the problem that is facing these analog processors? The problem here is that these scale poorly in space. So if we want to increase the matrix multiplication that's happening on this chip, you want to increase your inputs and your outputs, but they're increasing linearly, like on the edges of the chip. Whereas to keep it fully connected, most of the space is now being consumed by that array of weights, by that array of resistances. So your density of neurons, your density is actually decreasing as you increase your chip size. So this now, you have order and squared scaling in space. So you can't support a giant matrix in this architecture either. The largest ones are only a few thousand on either side. So that is the issue. We have all the die space is being consumed by this fully connected array of weights. So what people do is they keep their tiles really small so they can keep them dense. They tile many of them across the chip. They connect them with serial buses, and they call it a network on chip. And you have this local parallelism, but you're now globally serial. And you now have the same types of serial communication bottlenecks that you face in a GPU. Also, the largest matrix multiplication you can support is just not that big. So, these, while I think that, our friends down the street are doing some really incredible technology, they won't be able to fit like GPT-2 onto one of their pieces of hardware because it just won't scale up to support that parameter count. So this, of course, comes back to the question of, well, how can we scale up? How can we ultimately reach brain scale intelligence, or at least begin to get there by scaling up these core operations underneath neural networks? And of course, we looked to the brain, or Jack in particular, looked to the brain for inspiration. And the brain we see is fundamentally different. And of course, we'll come back. You'll see that all of these points have a theme. There's no fully connected regions in the brain, right? We've heard this many times today. The brain is very, 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 very sparse. There's a sparse connectivity. In particular, we see small world properties and even scale-free properties in the brain. But that means while it is sparse, it is very well connected. And of course, you also have sparse activations, as we talked about today. So to summarize this part, the scaling challenges of digital and analog approaches. Digital simulations are scaling poorly with time. Analog approaches are scaling poorly with space. But the brain scales with efficient sparsity. So now we'll talk about what we're building. Sparsity, our technology, and how we see the path to brain scale intelligence. So again, emphasizing the value of small world connectivity and why this is kind of a very special type of sparsity. If you have two opposing paradigms of fully connected versus locally connected, if you're going to fully connect a system, you'll have a very short path length, a path length of 1, from any point to any other point, but you're going to spend a lot on all the wires, right? All the connections. If you just want to be locally connected, you will save on your wiring costs. You can have less wires in that whole system, but the number of jumps to get from one point to any other point is not very large. So a small world network is kind of and many of you I imagine have heard of this, but it's kind of this universal network topology that you see across almost everything in the world. And it just emerges in so many situations. This is human social networks, electrical power grids, airplane mapping diagrams, the brain. But it is what it is you have lots of these local connections. Like if you're likely to be connected to things that are close to you, but you have a significant number, but very small number, of long distance connections. And that combination of lots of local connections and some long distance connections means you have a very well connected system. And this gives rise to like the 6 degrees of separation property among humans. Yeah, small world sparsity is everywhere. So when we think about our hardware, the key kind of insight that informs this architecture is that whether you look at biological neurons or if you look at a random mesh of nanowires overlaid onto an even grid of electrodes, they both possess small world sparsity. This was a paper that we published last summer. So this means that we can build a new type of AI processor, right? So instead of, we're using analog computation, we're using voltages and resistances to perform this matrix multiplication, but instead of the crossbar, which had only your neurons on edges, we fill the entire chip with these neurons. We go edge to edge, close pack them together. So we can have a huge density of neurons. And on top of that, we overlay this random mesh of nanowires. Connecting them is a small world network. So fundamentally, we're scaling a matrix multiplication. These core shell nanowires, because of their 2.5D kind of geometry, enable an interconnect density that you wouldn't be able to achieve using conventional CMOS lithography techniques. And as we said, we have constant neuron density now as the chip size increases. So we can fit tons of neurons and have layer sizes essentially in the millions, where today we're seeing layer sizes in the thousands at the most. So, and I like this. When I saw the picture of the Mark I perceptron, I just couldn't not use it because when we went to TSMC and we're like, we want to randomly connect functional components on a chip and put random nanowires, there were definitely some eyebrows raised. But what's so exciting is that you actually go back, and this was an intuition, this notion of randomness. Something that a lot of people have been comfortable with for a long time. We randomly initialize weights. We can randomly select neurons to drop out. And they randomly connected neurons in the Mark I perceptron as well. Go back here. All right, so these are some cool images, but this is a more realistic rendering of the first chip. So we taped out this chip, we're calling it Cumulus, in July. So it is a 100 by 100 grid array of electrodes, or neurons, if you will, which are really just there to kind of source voltages or read currents as inputs and outputs. and then we're placing on top this massive dense mesh of nanowires. And when we do that, here, so this is also a better rendering because it shows the electrodes. So we place the nanowires down basically onto the naked pads, and then we deposit metal to connect them. So even though they are stacked, we can get connections through these columns vertically and have a huge number of connections per electrode.
How big are these?
So these are 65 micron size, and this chip was actually taped out in a really big geometry, so 180 nanometer. But even with that, this is going to then support like a 5,000 by 5,000 matrix multiplication. So again, emphasizing the key pieces of brain inspiration that inform our technology. We're analog, we're aiming for low precision. There's been 6-bit precision that's been demonstrated in a large number of ReRAM, resistive RAM memristor stacks that we're utilizing, and of course we are sparse. So if we're going to compare to a V100 GPU, which of course is state-of-the-art for training, we do pretty well. And this is really just like our first coprocessor that we intend to commercialize. But if we're looking at an 80,000 by 80,000 sparse matrix multiplication with about 99% sparsity, we are, and again, ours is this will be in 65 nanometer, calling it Stratus, we like clouds. The V100 was in 12 nanometer, but we're operating at 2 orders of magnitude faster in speed and power consumption. And so we want to start at 2 orders of magnitude, but we have a roadmap to get even further, quite a lot further. So emphasize again the scaling comparison. When you're working in digital logic, you have order n squared scaling in time. When you're working with analog physics, you have order n squared scaling in space. But because we are removing what we believe are the redundant connections fundamentally in these networks, we can achieve order n in space and time, and we're the only chip architecture that we know of that can do so. The goal is to build really big networks. The first product that we want to bring to market is we're actually going to be relatively simple, aside from, of course, the MN3 itself. But really, we want to build a coprocessor to enable really efficient, really fast, massive sparse matrix multiplication. So we just want to do one operation. We want to do it really well. And because we'll just be doing that one operation, we're actually pretty agnostic to the compiler ecosystem. That means we don't have to build these massive kind of CUDA layers for this first product, and we just want to get it out into people's hands so we can start exploring what can we do when this is so fast and so efficient. And we're starting out with a 100x improvement on both speed and energy. Yep. And what I'd like to emphasize, of course, this is more than just neural networks, right? Matrix multiplication, sparse matrix multiplication can be used for a huge range of problems. Of course, the one we're most excited about and where we derive our inspiration is from artificial intelligence, but we think this will be used for a broad range of purposes, not just artificial neural networks. We're using memristors. Again, I just like that picture. We have this core shell structure. So what this means, we have a metal core and a shell that we coat, and we can create synapses that go through there. So our illustrator's on that. And yeah, and so this is something that's pretty interesting, and I may even call on Jack for a second to talk about number 3. But basically, our hardware supports a few ranges of models, and ideally even more. And this is looking further into the future beyond just our first product. But initially, we'll be able to demonstrate this within the next 6 months. This is called reservoir computing. Basically, you have a giant space of neurons that are randomly connected, and you can project an input into there, and then it puts that input into a higher dimensional space, so then it's more easily separable by a linear classifier. But basically, you don't have to train any of your internal weights. You don't have to have any control over the memristors, but it's actually a really powerful way to do time series classification. We want to support backpropagation. We do support backpropagation. We've tailored a type of backpropagation that works just on our chip. But the goal here is that we want to really just make it easy, so it's just you can make layers larger without having to change the fundamentals of neural networks. But in the long term, we are really, really excited about kind of bringing a new paradigm across the board. Not just about the hardware, but also about the algorithms. And there is this, we just filed a provisional patent on this last week, or at least the reduction of practice of an algorithm. And we're very excited about this, but it's energy-based models. And what energy-based models do, you define an energy function, and you tie the minimization of that energy to the minimization of loss in your network. And because we're building a physical network of resistors, we have a physical energy, and it's the dissipation of energy on this chip. So by tracing the dissipation of energy on this chip, we actually can understand how to train it and where the gradient is. We get the gradient for free, so to speak, by observing the dissipation of energy. It's an incredibly powerful thing. The immediate consequences of this are that we could be able to avoid the analog digital conversion from layer to layer, which currently for analog approaches for deep neural networks you need to do. That's incredibly energy hungry. So we could have very, very, very low energy consumption, like imagine 1 billion parameters on a form factor of a GPU. But probably the most exciting thing here is that by using energy-based models with a physical system and using physics, we now have the tools of physics to rigorously analyze the neural networks. We don't have a rigorous analytical tool set to really break down our deep neural networks today, but imagine we have like Maxwell's equations to actually understand what's happening in these neural networks. It could open up a lot of cool possibilities.
So this energy-based gradient, that's a pretty cool idea. And can it also update the quote-unquote weights in the same step, essentially? So you have to do a conversion for that.
That's just math, though, right? That's just math.
Yeah.
But the physical connections can't change, right?
Right, the physical connections are set, but the strength of those connections can be adjusted, right? Because we can adjust the resistors.
And that comes you down purely in this same step here.
Yeah, 2 out of 3 ain't bad.
Chad, do you want to throw anything in there?
Yeah, you basically, a lot of these energy-based models, they have problems with inference speed. But if you say that you can actually show, we actually just showed this, I'm working on a paper hopefully with one of Joshua Bengio's students right now, showing that you can formulate a physical network, and that physical network will minimize its power dissipation. So if you have an electrical network, it will naturally minimize its power dissipation. But it does so like practically instantaneously. So that's the amount of time that it takes to perform inference in an energy-based model, and that's the core limitation of these energy-based models. So if we can make that settling to that energy minimum much faster, we can potentially make these models useful. So that's really
cool. So in the future, we're building first a coprocessor with PCIe slots, but we want to build ASICs for all types of applications, not just embedded, but we want to build robot brains. And we would like to ultimately become the next platform on which all artificial neural networks are built. We're certainly not wanting for ambition. And yeah, we envision a world where massive models can fit in the form factor of a GPU, because ultimately, that's a world that we already live in already, because those are our brains, right? We have billions and billions of neurons and nearly quadrillion synapses, and we do it, so why can't we do it in hardware? So that's all that I have. I do have like these market slides that may feel a little pitchy, and I'll skip all this. But no, but happy to take any questions you guys have about the hardware, or you can direct it to me or Jack or whoever.
My question is, so your process is 100% analog process?
Right, so the matrix multiplication is analog. So
what is digital?
So we have digital analog converters kind of in the front that will take any type of input array and convert that into like 6-bit analog signal, and then we have analog digital converters in the back which read out the currents and then convert that back into a 6-bit signal that goes back.
But that will contribute the power, right?
Yes.
Yeah, absolutely.
You can actually do it extremely efficiently. You can do it extremely efficiently. We have all of our power consumption estimates include ADD and DA conversion.
So even with that ADC, DAC stuff, we're looking at starting at 100x.
Yeah, the energy-based model will remove all of that from the interior of the network.
Yeah, that down the line.
So let's say you tell me the connectivity structure imposed by these wires, and then I look at that really carefully, and I give you back like the resistance values I'd like. Can you just program those?
Yeah, I was wondering about that.
Yeah. Yes. So we can. So one of the big things that we've been excited about over the last year is that we cracked how to do model transfer. Yeah. It's been a big issue, right? Because every chip actually, because it's random, ends up being a little bit different. But provided you have high enough density and even enough distribution of the wires across the chip, you can map a matrix of effective resistances. And it's about the effective resistances between any two electrodes, and you can just nudge the weights as we do. We pulse voltages to raise the resistances of the membristors or lower them. You can kind of upload an arbitrary resistance matrix to one of these threes.
Oh.
What about negative numbers?
Yeah, we deal with that by, there are a couple ways that you can deal with that. The most naive way is to simply double the number of outputs that you have, and you subtract the two at the end. And that way one acts as your positive weights, and then the other one acts as your negative weights, and then you just take the difference of those.
The wires connecting are different, but you assume that doesn't matter.
Yeah, it doesn't matter because the like the effective resistance into one, you can manipulate independently from the effective resistance into the other.
So your manufacturing process actually allows you to have a random.
Right, so that's part of the, so currently we do those wires ourselves. Nikita is an incredible fabrication engineer. So the whole idea here is that if you're using masks,
you pick a random wiring and then you just
well,
print that.
no, but the thing is, if you're using a mask and you're using lithography, the number of layers that are required would just exceed by, by a huge number of the amount, the density of the wires we have ourselves. So what we're doing, there's a top-down method for manufacturing wires, where we get wires that are really long and really thin, and then we make them core shell wires with the fabrication method and place them onto the chip at the end.
It has some variation in it.
Yep.
So you mentioned you have 99% sparsity. That's the
Yeah. So Stratus will have 99% sparsity, and that's a 400 by 400 grid. But I mean, really, we're limited just by how much we can stack up, the wires. So we could play around with the sparsity and get like a lower sparsity if we wanted to. Of course, smaller chips will have a lower sparsity amount. But I think we're aiming to going all the way to like
one of the broad intuitions is the width of the layer increases. You can get away with higher sparsity.
Yeah.
You can also aggregate, so you can do like multi-compartment neural models, and so you can combine like 4 electrodes into one neuron, and you can have like 1 output and then 3 inputs, and then you can combine the synapses from each of those to dynamically adjust your sparsity.
Now you're speaking our language.
Yeah, you can get by with higher sparsity with more dimensions essentially, but there's still a floor.
Sure.
I mean, you still 1 by 20 or so at least.
About 1,000.
So one of the questions I had is, as you designate which are input and which are output electrodes, do you have a planned distribution in mind, or they can be ambivalent?
So it depends, right? We think probably the most intuitive way is actually to alternate input to output, because then you kind of have some topological preservation of the network itself.
For images.
For images.
So one broad comment on sparsity actually is I think you can get away with, to a large degree, fixed sparsity if you exploit the topology of the data. So if you look at convolutions, like convolutions are fundamentally sparse operations, but what they do is they reflect the topology of your data. Right? There's a 2D structure to your images, and convolutions are just breaking that up in a sparse way to naturally operate on things that are most likely to be correlated. So I think that if you make we have this like 2D structure, and if you create, if you like self-organize your data before you project it here into this map, I think that you can get away with basically sparsity. There's a way to map that's efficient, that reflects the topology, and that's the way that you should do it. Right now, we're just randomly mapping because it's easy and it works.
Yeah, still trains. Yeah. Okay. Thank you guys so much. Appreciate the time.
That was our last presentation. I'll be here for about 20 minutes more, guys, and have meetings and
yeah.
Thanks a lot for your attention.
Great, thank you.
Lucas?
Was that one question?
Oh yeah? That's a great question.
So, last meetup that Lucas organized, we had like 10 people here, 15 people here. Now we have, what, like 40 people, 30 people?
Yeah.
Which is great. This room obviously is not perfect for that. So my question is, does anyone know of a place where we might be able to meet next? Or is anyone willing to host a next meetup? If we keep growing this is probably not an ideal space. But if anyone knows of something or the company can host it, that would be fantastic.
have a large venue, but it's 20 miles south
We have a space we could use. We have like our main sort of old hand office.
Oh,
workshop.
okay.
You know, the seating might be
It's like
about
5 minutes away from
We're
here.
like, yeah, just up the street.
And could you fit about 40, 50 people there?
I don't, we need to get by some more chairs. But,
Well, we could bring some chairs
Oh,
up.
yeah, in that case. Yeah, I think so. Let's, well,
Okay,
I'll,
that's a possibility. If anyone has any other ideas too, I think Lucas.
Yeah, please message me after Meetup. I have some cards here. Yeah.
Thank you.
Thank you guys.
Yeah.